Hi there, welcome to the Electronics Lab. In this video, I'm going to work through a couple of practice problems with series and parallel capacitors. So let's get started.
We have charges like electrons, with a force which is enormous.
So in this practice problem, we have three capacitors in series, and what we want to figure out is the total capacitance of those capacitors, the voltage across each one of the capacitors, and then the total charge that's stored in that block of three series capacitors. So to start with, the total capacitance. When you have capacitors in series, that total capacitance is equal to the sum of the inverses of the individual capacitors taken to the power of negative 1. Or another way to put it is it's 1 over the sum of the inverses of those capacitors. So then this will be 1 over 10 nanofarads plus 1 over 20 nanofarads plus 1 over 22 nanofarads, all taken to the power of negative 1. So after all of that arithmetic, we find that the total equivalent capacitance is 5.1 nanofarads. Let's jump down to calculate the total charge. Remember, with series capacitors, the charge on each of the individual capacitors is the same, and it's equal to the charge that's across the equivalent capacitance. So total charge, when we're dealing with capacitors, will be the total capacitance times the total voltage. So this is going to be my 5.1 nanofarads times, oh, I forgot to add one important thing, 9 volts across the whole circuit. So 5.1 nanofarads times 9 volts gives us a total charge stored in those capacitors, 4.59 times 10 to the minus 8 coulombs. And remember, Qt is equal to Q1 is equal to Q2 is equal to Q3. So that's also equal to C1 V1, C2 V2, C3 V3. And if we go back to the original equation, that's total capacitance times total voltage. So all of those pieces are equal to each other. So now we can use this information to figure out what the voltage is across each one of these individual capacitors. The total voltage is 9 volts, but that's not evenly distributed amongst those capacitors. It's going to depend on the capacitance. The higher the capacitance, the less voltage will be across it. So let's use that information to calculate V1. V1 will be equal to total capacitance times total voltage divided by C1. That was just taking this part of the equation and just rearranging it for V1. So that will be 5.1 nanofarads times the 9 volts divided by 10 nanofarads. And that works out to 4.59 volts. Okay, do the same thing for V2 and V3. So V2, that's going to be CT VT equals C2 V2. So rearranging that equation in terms of V2 gives me total capacitance times total voltage over C2. .30 volts. And I'll do the same thing for V3. So we've got V3 is 2.09 volts. Now let's do a quick check. Using Kirchhoff's voltage law, the total voltage is 9 volts, but that should also be equal to V1 plus V2 plus V3. I mean, I've already got the answers here, but it's always a good idea to do a check approaching the problem from a slightly different point of view and making sure that you get the same results. So V1 plus V2 plus V3, we have 4.59 plus 2.30 plus 2.09, 8.98 volts. I'm 0.02 volts off. That was because there was some rounding that occurred when I did these calculations for the voltages. All right, let's move on to the second problem. So I've got a parallel circuit this time, 3 capacitors in parallel. The capacitor values are actually all the same as from the last problem, but this time they're in parallel. And let's say we've got that same 9 volts across those capacitors. Because they're in parallel, it'll be the same voltage across each one of them. And again, we want to figure out the total capacitance, the voltage across each one of the capacitors, and then also the charge that's being stored on each one of the capacitors. Well, the first thing that's the easiest thing, the voltage across each one of those capacitors is 9 volts because they're in parallel. So that one's an easy one to figure out. The total capacitance is also really easy to figure out. When you have capacitors in parallel like this, the capacitance is equal to the sum of the individual capacitors. So the total capacitance is 52 nanofarads. The total charge that's stored in this system of the 3 parallel capacitors will be the total capacitance times the voltage across them. So the total charge stored in the system is 468 nanocoulombs. And now let's do a double check by figuring out the total charge in each one of these individual capacitors and then making sure that the sum of that also adds up to 468 nano. What's that called? A nano. That's a nanocoulomb. There we go. Okay. Charge on capacitor 1. That'll be the capacitance of it. So 10 nanofarads, and the voltage across it, 9 volts. So that gives me 90 nanocoulombs. Q2, again, capacitance times voltage. And Q3. Okay, so we have the charge on each one of the individual capacitors. Now let's add that all up. And I get 468. These are nanocoulombs. And that totally matches up with what I calculated when I did the individual calculation for the total charge stored on the system of capacitors. And that's it. We've gone through a couple of practice problems, one with series capacitors and then one with parallel capacitors, and we calculated the total capacitance of the system as well as the voltage across each individual capacitor, the charges stored on each individual capacitor, and then the total charge stored in the system. Don't forget to like the video, that helps others find it. Subscribe to the video if you found this content interesting and you want to get more of this kind of content. And I really appreciate you watching. See you next time on the Electronics Lab. Bye for now. Hi there, welcome to the Electronics Lab, where it is my job. What is my job? To help you through your engineering courses.